we will now turn our attention to the idea of optimization problems. Now, you've dealt with a lot of optimization problems back in algebra. It's the sort of thing where you probably remember you have 150 yards of fence, and you're going to build a corral where a river runs along one side. So what's the dimensions of the corral to get the biggest area for the horses? You've seen that a lot in algebra. And you're always limited to only being able to work with basically quadratic functions. And we will be working with quadratic functions here, but the techniques that we're going to talk about will allow you to work with many different type of functions. You won't be limited to simply quadratics to solve now. And the process that we will go through based on derivatives will be much, much faster to solve, easier to solve than the old algebraic approach. So, in terms of learning objectives, what you want to do is simply want to solve applied minimum and maximum, which are referred to as optimization types of problems. Now, before we actually get into an example, let's just talk briefly here about some basic guidelines to set up optimization problems. If you kind of follow these basic steps, this basic concept, then doing the problem is typically a lot easier. So first thing, I want to read the problem and identify all of the variables and all of the constants that I need to be working with. Next thing I want to do is, if at all possible, draw a picture. This is a biggie, guys. If you can draw a picture of what it is you could be dealing with, 9 times out of 10, the picture will actually tell you how to solve it. I want to identify the objective function. The objective function is a function that we're going to optimize. The objective function is terminology that says, hey, I've got this function, whatever it is, and I want to optimize it. And I want to write it in terms of variables that you've identified in the problems. So when I go through and I pick out all these variables, I want to write this objective function in terms of those variables. I want to identify all constraints. I'm writing them in terms, there should be an I right there, sorry about that, in terms of variables that you've identified in the problem. So the constraints, like the fence on the river problem, if I have 150 yards of fence, that's a constraint. I can't go more than 150 yards. And obviously I'm not going to do less than 0. So those would be constraints on the amount of material that I have available. Now I want to use a constraint or constraints to eliminate all but one of the independent variables. Typically I'm going to end up with 2 or more independent variables, and based on the constraints I should be able to eliminate all but one of them in the objective function. And then I'm going to simply use calculus techniques to find local, if appropriate, absolute mins and maxes of the objective function on the interval that we're interested in. So to maximize or minimize these things, all I'm going to do is take the first derivative once I get this objective function written in terms of only one variable. So let's start off with a quick example here. I want to maximize the area of a rectangle that has the perimeter of 64 feet. So right away I'm going to draw myself a little rectangle here. And I'm going to label that. I'm going to call this H and this L. And then I know that I'm supposed to maximize the area. So the area is going to be H times L. Well, right away I know I have a problem to have 2 variables here. I really need to get this in one variable. But I have a constraint. The perimeter is 64 feet. That's a constraint. The perimeter is going to be twice H plus twice L. The perimeter is 2 times H plus 2 times L. It's all the way around. But I know that that perimeter is actually equal to 64. So what I'm going to do now is I'm going to pick a variable. It doesn't matter, either L or H. I think I'll go ahead and work with L. And I'm going to write L in terms of H. So I'm going to solve this for L. So that means L is going to be equal to, what do I have? 64 minus 2H divided by 2. Obviously this is going to cancel and give me 32. So this would be 32 minus H. This is now L. So I can take that L and substitute it in for my area. When I do, I get area, which is now a function of H, is going to be H times L, but L is 32 minus H. So there's my function of H. And I'm going to write this as 32H minus H squared. So what I really need to do now to find a maximum, well, this is just a function. This could be x if you wanted to. Find the derivative. So I need dA dh. I want the derivative of the area with respect to h, which should be 32 minus 2h. And just like we did before, when I need to maximize a function, I'm just going to set this to 0 because that's going to give me my candidates for mins and maxes. So if I take 32 minus 2h, I set it equal to 0. That implies negative 2h equals negative 32, which implies h equals 32 over 2, which is 16. So there is a critical value. As a matter of fact, it's my only critical value. So just by the nature of this problem, 16 has got to be what maximizes this. But I'm going to play it safe. I am going to check it. So I'm going to take a look at the first derivative, and I'm going to look at my critical value, 16. And I need a value less than 16. And obviously, h has to be on 0 to 64. So I'm going to pick 1, only because that makes evaluating the first derivative really easy. And right here, where is it? Oh, right here is my first derivative. So when I put 1 in there for h, I end up with a positive value. When I pick a value bigger than 16, like I don't know, maybe 17 or something, when I put that in there, I end up with a negative value. And that's all I care about is the positive and negatives, because I know now that my function is going from positive to negative, and it is 0 when h equals 16. So that tells me I have a local max at h equals 16. So now all I need to do to finish this up is figure out what the length is. Well, I go right back to here. I know that the perimeter is going to be 2 times h, which is 2 times 16, plus 2 times the length, which must be 64. So then I finish this up, and I find out that the length is also going to be 16. So what this is telling me is that the area is maximized when I'm restricted to 64 feet of perimeter. The area is maximized when the height is equal to 16 and the length is equal to 16. So in other words, when the rectangle is a square, a 16 by 16 square, the area is maximized.